Good afternoon, everyone. I'm Cassie with AABC, and I'd like to welcome you to today's Tab Talk webinar. I also want to thank our sponsor, Evergreen Telemetry, for supporting this session. Just a few items to cover before we get started. Our presenters will be holding questions until the end of the presentation, but we encourage you to submit them at any time using the Q&A button at the bottom of your screen. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists so that our producer, Will, can assist you. This presentation is being recorded and will be available for viewing in 1 week. In terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. And finally, if you're a certified TBE or TBT, your CEUs for attending any webinar in this series will be automatically uploaded to your respective portal after the webinar. Today's webinar is Tackling the Challenges of Repeatable Ultra-Low Flow Measurements with Eric Grundmeier, President of RSAnalysis, and Pete Secor, founder of Evergreen Telemetry. Eric Grundmeier is the president of RSAnalysis LLC. In 2012, he joined RSAnalysis as an apprentice, and his dedication quickly led him up the ranks. By 2017, he became a certified AABC test and balance engineer. In October 2022, he was promoted to president of RSAnalysis and is now focused on growth and ongoing improvement across the organization. Pete Secor founded Evergreen Telemetry after a career in semiconductors, systems, instruments, and wireless electronics. He was and still is driven by a passion to provide faster, easier, safer tools for the tab industry and beyond. Without further ado, I'd like to hand it over to Eric and Pete to kick us off.
Morning, guys. Just getting our slides up here. It might be afternoon where you are too. Hi, guys. Thanks for joining today. We're going to be talking about measuring low flows. Pete Secor here. We're going to be going over a case study that Pete partnered with RSAnalysis as we were brought into a lawsuit or litigation between a school district and a manufacturer. We called on Pete to help us out, and we just got done here right before this is my first webinar. And right before this, we had a little, practice session. And one of the things that, I hear about Pete all the time is that, he loves talking test and air balance, loves talking air flows and everything else. And it's true. I had an experience in New York City where we met Brian Sabian. He was the general manager of the Giants, and we got to meet him, and what a likable guy he was. And he just loved talking baseball. And I say that about Pete too. He loves this industry, and it was a great to get to chit chat and talk and go over our slides together. So one of the things that I wanted to bring up here in the beginning is that, testing low flows is not something new, right? That's something that has been going on in our industry. But I do think that what we're seeing, and I'll hand it over to Pete here, is that we're seeing an increase in that request where, Pete didn't start updating his technology just because he wanted to, is that he's actually seeing requests in the industry. Is that right, Pete? You're on mute, Pete. Pete, you're on mute.
How's that?
Perfect.
Yeah, a few years ago, we were challenged to get down to the 30 CFM area, and we came out with our low flow capture hood to be able to do that. At the time, it was unimaginable to me that a test and balance technician would be required to measure something down around 30. But as the industry is getting more and more interested in energy savings and not wasting, conditioned air, everybody's wanting to measure in lower and lower flow. And we have heard just recently in the last 12 months or so about more and more applications that for some reason want to measure down around 5 CFM. Perhaps it's a bathroom, perhaps it's some sort of storage closet or whatever. They just don't want to waste, let's say, 50 CFM of air if 5 CFM of air will do the job. But how in the world are you going to measure something that low? So that's what we're going to get into here in a minute. But I appreciate the challenge, and thanks for the opportunity to work with Eric on this particular project.
Yeah, there's not too many equipment providers, guys, that give this level of service and help you with projects like this. And Pete's one of those guys. So highly recommend always reaching out to him. I know when we were out in Arizona, he offered for anybody that, we had the AABC conference out there and anybody wanted to go by his facility. I'm sure the offer still stands. So if you're in
Yeah,
Arizona, go see
absolutely.
Pete.
Very, very
So a
proud of our
little,
new factory.
Yeah, so a little bit about the case study. So we were approached by a mechanical engineer of record, and basically what had transpired is during COVID, there was a manufacturer that went to a school district and they had a device, a purification device that had all these promises about pathogen elimination and how they could do it through these low flow, 100% recirculation devices that they would go in, install in these schools, in these classrooms. They were 120-volt devices that basically you could just plug in, and they were in the ceiling. They had these 2-inch tubes that went out, and that was the promise. And so the school district ended up getting involved with this manufacturer, spent about $6.5 million to get these into all their classrooms with, basically, and the school district was trying to do something that was correct and right, was trying to protect students, trying to protect teachers. What we quickly realized is that the promise or the expectation versus reality was much different. So our involvement was the MEOR, who was hired by the litigation team, came to us and said, hey, I need you to go out and either prove or disprove this piece of equipment. So we had this device. Basically, as we got the literature back to us, our expectation at the onset was we were going to be reading somewhere in the realm of 75 CFM per outlet, with a total for the device of 300 CFM. That was kind of the expectation. We were going to go through some, they actually gave us one of these devices and we were able to do some bench testing here in our lab and go through it. So what we quickly realized was the expectation versus reality was much different. And the reality was that we weren't getting 75 CFM per outlet. These units were not doing 300 CFM, but they were doing much less. And the outlet CFMs were all below 10 CFM. So this is when we were going through some different iterations on how to measure this flow. And we had 600 plus diffusers that we had to go read. So, trying to create, we created a little plenum, a 4x4 plenum, in which we were trying to read the, a pitot traverse as we taped it to the ceiling, and it was just not, it wasn't working out. So that's where we got Pete involved, and Pete was willing to, he was in the midst of creating the low flow plate and was able to send somebody up here to help us out. Pete, anything you want to add there?
Yeah, it's a very, very difficult challenge when you're getting down underneath 30 CFM, and we'll talk in a minute about how we address that. But it was a very interesting project, and appreciate you calling on us. And in the future slides here, we'll talk about how we did it.
Yeah, and some things, as we looked into this manufacturer's published data, even with us achieving this 300 CFM, the other thing that came to light was you were only at that 300 CFM for the classroom. You were only getting about 2 air exchanges through this device, and their promise, and I'm sure a lot of us experienced this throughout the industry during COVID, and it really highlighted airflows and IAQ and things of that nature during that time, was that there are a lot of these manufacturers coming out with all these promises, and we know that 2 air exchanges is really next to nothing, and when we got down to the actual measurements, that were total for the device was 15 CFM, you're talking below a 1 air exchanges in the room per hour. I mean, these things were just not doing much. So want to talk about some of the challenges that we faced, challenges with accuracy. We have equipment limitations, and Pete's going to touch on that. And even what I wanted to bring up with like the environmental sensitivity also is that, when we're we're asked to measure low flows to when it comes to package units and outside airs, right? And those environmental impacts, meaning if we have prevailing winds, can really change how we're measuring. And the last piece of this puzzle, and the one that I highlighted here, was the repeatability aspect of this project. And what, out of all these challenges, that's really the one that we focused in on, because we were basically in the court of law saying, here's our readings, and they have to be repeatable. And that's something that's across our industry that we really hang our hat on, is that our readings have to be repeatable. So we're getting into these really low flow challenges, and we needed some efficiency in measuring these as well. And that's really where, Pete came into light with, being able to use his hood and have some repeatability to our methods. And so the repeatability aspect is, we needed consistent results. We needed reliable data and credibility. So, having Pete on board here really helped us with our credibility, especially with the mechanical engineer record that we were working with. And Pete, explain to us some of the challenges with repeatability when it comes to a flow hood, velocities, velocity pressures.
So our technology is pressure-based. We're going to measure velocity based on velocity pressure. When you're talking about low flow, you're talking about low velocity. There's a certain minimum that sensor needs to see in order to get an accurate answer within a reasonable time frame. So as an example, if you're measuring with an airfoil or a pitot tube at about 100 feet a minute, you're looking at a signal that's, in terms of inches of water column, that's 0006 inches of water column at 100. So that's somewhere in the range between 75 feet a minute and 100 feet a minute is where you need to be at a minimum in order to get a reliable answer in a few seconds. If you're lower than that, you can improve your consistency if you measure over a longer period of time. Instead of 2 seconds, try to get to 6 seconds, 8 seconds, or even average 5 readings in a row. In order, if you do that, you'll get consistent results. But that's what you need to do in order to measure low. I've got some actual facts and figures coming in the next few slides.
Yeah, guys, in the repeatability aspect, when we were dealing with this with the MEOR, they were saying, how accurate are these readings? And whether we were, 5 CFM per outlet, 7 CFM, 10 CFM, I mean, these are just crazy numbers, as we all know, is, trying to measure that, it was probably in that range, right? We were comfortable that it was within the range of, 5 to 15. We had done our multiple data sets to prove that that's the range that we were in. But the repeatability aspect was so important to, the lawsuit basically that we were a part of, because, if it's subjective, then it gives them that ability to say, well, your readings are subjective, right? So being able to go back and prove that, hey, we read 7 CFM and, we are right within. And I will tell you, we beat this up pretty bad, and we were able to repeat those readings within a margin of error that was just incredible. For such low flows to be able to go back and repeat those readings, with a capture hood and the low flow plate was just it was incredible. So hats off to Pete here for his help with us in that.
Thank you.
So here's an example of what Pete was talking about, guys, and where this repeatability. Our first attempt with the 8-inch hood, you can see the velocity pressure at which we were trying to read at that time. We are way out there, 4 zeros, 7.6 with trying to read this, 7 CFM, and that's just with our devices, in just any kind of changes in a system. I mean, this one wasn't changing much, but we do have, other places where we see system changes. This one was pretty stable and we were in a stable environment, but still that's just too much for our pressure sensors to try to keep accurate and, repeatable. And then once we got the low flow plate, you can see how our velocity pressures change. So, this is where I'll hand it off to Pete to kind of explain more of, what he's targeting here.
Yeah, what you have to accomplish when the airflow is very, very tiny, in order, again, to measure a minimum velocity pressure, which equates to a minimum velocity, you got to keep the velocity itself. You have to keep it up over 75 and preferably over 100 feet a minute. At 100 feet a minute, you can measure accurately and consistently in 2 seconds. At 75 feet a minute, you want to take 4 seconds, 6 seconds. You might want to go a little bit longer in order to get consistent results. So how do you do that? You have to somehow shrink the area. So in a future foil, we'll show how we went on our low flow capture hood that we call the 8-inch diameter 8D. We introduced a flow adjustment plate that reduced the effective area. So at a very low CFM, we could keep the velocity up where it could be quickly and accurately measured. And then everything is verified on a NIST traceable traverse with a long straight duct. So the credibility is there vis-a-vis NIST, and just making sure that the area of the capture hood is appropriate to the amount of CFM that you're trying to measure.
Yeah, and guys, this application was specific to this case study that we were a part of. We're going to get into more of some of the applications that we see coming up in the future of test and air balance and where this, may be leading for future, because, Pete touched on it in the very beginning that engineers are trying to reduce that CFM value, for energy conservation. So can we keep, people comfortable? Can we keep them safe? Can we get those minimum air exchanges? And how far can we take that until, we start to compromise any one of those things for energy conservation? So we definitely see that there's going to be an uptick in this request of, having to measure and repeat these low flow values coming up in our industry. Moving on, we got some information from Pete here about what he's developing in his capture hoods.
Right. So obviously, CFM, cubic feet per minute, it equates to the velocity in feet per minute times the effective area in square feet. So as the airflow in CFM gets lower and lower, the velocity pressure gets lower and lower. So we use a grid arm, and the ability of the grid arm to detect velocity via velocity pressure is very similar. So a lot of people are familiar with, well, first of all, the pitot tube. The airfoil does a little bit better job, and the airfoil, the face velocity grid, and the measurement grids that are used in capture hoods all have about the same ability to detect velocity at a particular level relative to the velocity pressure. Foil probes create a certain velocity pressure at a given air velocity. So for instance, at 100 feet a minute for an airfoil type device, you're generating a 0008 inches of water column. At 75 feet a minute, you're only generating a 0005. So the sensor that we use is working pretty hard in those cases, very hard if you're looking at a 0005. So in order to get down to 30 CFM or 5 CFM, you're going to have to do something different. You're going to have to shrink the area involved. And Eric, if you go to the next foil, this describes that. So a traditional capture hood, our traditional capture hood, we call it the 15-inch diameter. It's very similar to the standard short ridge hood, the standard TSI hood, where the capture hood area, the effective area, is about 1.1 square feet. So at a nominal 100 feet a minute, you're looking at 110 CFM, far, far higher than we're wanting to measure in these special applications. So our low flow capture hood, we call the 8-inch diameter, shrinks the effective area down to 0.2. So again, at a nominal 100 feet a minute, you're looking at a 20 CFM there, and at a 75 feet a minute, you're looking at a 15. So you can measure quickly 2 to 4 seconds, consistently get exactly the same answer over 10 readings in a row at somewhere in the 15 to 20 CFM area. And finally, that wasn't going to do it for Eric's application. That's the lowest product that we had up until about a year ago. And Eric came along with a potential requirement to try to get down to the 5 CFM area. So the only way we could do that, this is our base for our low flow capture hood. It's got 8 inches in diameter here. And as you said, the effective area there at 0.2. We had to somehow shrink that effective area. So we came up with this flow adjustment plate. It mounts inside the capture hood, and it reduces the effective area down to just 0.05 square feet. So again, at a very low CFM, you can keep the velocity that's being sensed by the grid and the electronic sensor. You can keep the velocity up around 100 and still be able to measure a tiny 5 CFM. And as I said, we verified the accuracy in a long straight duct with a NIST traceable pitot tube. So that's it. I just want to quickly mention while we're on this for back pressure. Okay, the thing you got to watch out when you're going to have such a restrictive area is that the flow really does need to still be tiny. If you were trying to measure 100 CFM with this plate in place, you would quickly, the air would build up behind the plate, it would back up into the supply duct, and it would cause the air to, if it would cause the air to go somewhere else. So what you measured would be accurate, but you wouldn't realize that the air was going somewhere else, and you would be misled by that. So there's a range in which this type of a plate would be effective. You have to be monitoring that and make sure that you really are talking about 5 CFM, 10 CFM, 15 CFM, and not 50 or 100 CFM. If you do that, you'll avoid the back pressure problem, and you'll get a very accurate answer and an answer that can be consistently repeated.
And one thing that we brought up in our practice session here, Pete, and I wanted you to touch on this as well, is the trending or the how long duration, right? So when we go into the Evergreen risk reporter, we can select, is it every second, every 2 seconds, every 4 seconds? We were talking about that over time average over, a reading like that can help kind of even out that reading, because we do have changes, and especially going into, I know for myself that we've had CX agents, look at our meter with us as we're trying to read a diffuser as we're going through tab verification, and they start questioning, well, why is your meter going from 300 to 315 to 310 to 305? Why do you have all these adjustments and changes? And we talked about this a little bit, just kind of how VAV's fans are changing, and the velocity pressure we're trying to measure is so small that we're going to have those changes in our meters. And why it's so important to understand, as a second point to this, is it's so important for new technicians to understand how our devices work, right? You're capturing this airflow with a capture hood. It's going through a measure grid. That's going into a pressure transducer as a DP. You're calculating it based on an area. You're coming up with a velocity times it by the area of the base of the hood, and that's giving you this CFM. So I guess kind of two questions there is, we'll start with the 2 to 4 seconds and just kind of expand on that.
Eric, I don't know if it's convenient if you could go back to the previous slide about the velocity pressure. I'll talk to that. So we're talking about the grid. The grid is, there's going to be a certain velocity of air across the measurement grid. The measurement grid is going to provide a velocity pressure to the electronic sensor. If you're, just imagine for a minute that you're at 1,000 feet a minute, you're talking about a pressure that might be 0.1 inches of water column. Certainly it's going to be above 0.01 inches of water column. Super easy to measure, and one that doesn't vary so much. So when you think about what's going on in the environment where a tab technician is doing his job, he's got the system, he's got dampers, he's got VAVs, he's got people moving around in the building, doors are opening and closing. When you're at 1,000 feet a minute, the signal is so strong, it's relatively unaffected by everything else that's going on in the building. And you're going to get, without doing anything, in 2 seconds, you're going to get consistent results time after time after time. But when you're down, let's just imagine you're down at around 100 feet a minute or even less. What's going on in the system is variation. That grill, you want it to be 100, you think it's 100, it's never 100 consistently. It's always doing like 90 1 second and 110 the next second, because it's affected by everything else. So the real world is not consistent when you're talking about 100 CFM at a particular grill. So the electronics will sense that. It'll accurately tell you that 1 second you're at 90 feet a minute. The next second you're at 110. If you average over time, and we do give you the ability 2 seconds, 4 seconds, 6 seconds, 8 seconds, we give you the ability to take a longer look at that. That'll give you a much more consistent reading, even at 100 feet a minute. And then what I'll often do is just average 2 or 3 or 5 readings in a row, average those, and you're going to, if you're at 100 feet a minute or 100 CFM, you're gonna get very, very consistent readings, because over time, it really is 100 CFM coming out of the grill. But for any 1 second, it's not 100 at that particular point in time. So that's what's going on when these velocity pressures are really, really small. Not only are they hard to distinguish by the sensor, but what's going on in the environment is causing them to change from 1 second to the other. So averaging allows the sensor to do a better job, and it allows the tab technician to realize what's happening in general, or what's truly representative of that particular grill over a period of time, and not just a snapshot, not just a 1 second snapshot.
Yeah, and I think that is so important for us to all understand, especially as we're going out into the field and using our capture hoods to measure. I mean, as much as we talk about how accurate we can be with a capture hood and those type of things, I mean that is the direction this industry is pushing us with tab verification, right? I mean, when we go out with commissioning agents or IORs, mechanical engineer records, and we're proving and showing our readings, they want to see that reading on our devices. And the more stable we can make that for them, because it's hard to explain to them when we're talking about the velocity pressures that we're talking about here, especially at the low end of these devices. It's so easy for it to swing that variation, and it seems like a lot when somebody's looking, you're looking at it and you're saying, oh, you went from 100 to 115. That's a 15% change, right? And it's like, well, let's really look at what the velocity pressure is, because it's so small at that level. It's really not changing that much, and it's very easy for system dynamics to just change and to have those variations happen. So I definitely think that over having that duration, the multiple readings over a duration to kind of even it out really helps kind of prove our readings when we're going through balancing, which definitely helped us, when we went back and had to prove our readings during this case study. They, being able to come back and have those same accurate readings that were what we reported was so important.
Right, I agree, Eric. And one of your slides talked about credibility. The tab technician wants to have the feeling that he's getting a good, solid answer, which a consistent result can give you. But also the auditor that comes up says, "Okay, show me what you got." If you get the same consistent reading time after time after time, that's the credibility. So the tab technician can realize instead of trying a 2-second reading, go with a 8-second reading, and if possible, average it, average multiple readings. Boom, that's your consistency, that's your credibility right there.
Yeah. And so I know we have some more slides here.
Yeah,
Pete.
just some a show and tell. So this is relative to getting the right answer at very, very low flows. You can see that the full-size capture hood is much larger. It's designed for higher flows, whereas the low flow is much smaller, and it's designed for those low flows. This particular one is designed down to 20 CFM there on the left.
And this just, illustrates to, in our industry, having the right tool for the right job, right? That,
Right.
when you're trying to measure, we're going to get into more of the application base of low flow testing, but we've all been in the scenario where, you have a bunch of bathrooms all at 50 CFM, right? Having that ability to use the right tool for the right job helps you have that repeatability, that credibility that we're talking about. We can go back with that same tool, have the same measurement, which really proves in the value which we bring as test and air balance.
Right. Energy efficiency, number one. And number two, a lot of dollars that are being provided under the condition that the building is going to be energy efficient. So how much outside air is being brought in? How much air is being provided to a storage closet? But what's the exhaust fan in a bathroom doing? More and more people are trying to be very, very accurate on tiny airflow numbers that wasn't the case 5 years ago. So we have since yours was the very first time anybody asked us to measure down around 5 CFM, but since then we've had 3 or 4 others, and we've been able to provide a solution because we had it ready in your particular case. I would say it's still not widespread, and it's a difficult challenge, and it's not one that a lot of people want to take on. But there are situations here and there where an auditor or regulatory authority or whatever wants to see a reliable reading at a very, very tiny CFM. So now, because we did it for you, Eric, we're prepared to do it for others.
Back slides here. So this was the example I think you were showing of, and then we have a next picture that shows this actually installed. But this is the low flow plate and the 8-inch hood, correct?
So on the left side, that's our standard low flow base with no skirt attached, with an effective cross-sectional area of 0.2 square feet. So at 100 feet a minute, it's 20 CFM. And then the plate next to it reduces that effective area down to 0.05 square feet. When I say effective area, instead of just measuring and calculating the area, what we do is we put the hood on there, and we traverse the duct, and we make sure, let's say that we're pushing 100 CFM through a particular capture hood. And then we switch the mode over to velocity, and we measure velocity. And then we just take the 100 CFM and divide it by the measured velocity. That gives us the effective opening. Anybody out there can do the same with Shortridge or TSI or ours. You can do it on one of your test ducts. Measure 100, switch the mode to velocity, make the division per the equation there, and you'll come up with the effective area. So you're not trying to figure out what's the open space of these geometries.
We do have it, the installation here.
Yep. So you go ahead and install that. I call it a flow adjustment plate, or flow range adjustment plate. So I'm gonna change the range from 15 CFM and up. I'm gonna change it to 4 CFM and up. And you can see the little orifices there that are capturing the velocity pressure from the passing air. and giving the signal over to the sensor on the side.
Well, this was the comparison. Sorry, there's one more slide.
Yeah, this is just a visual of what we've been talking about relative. This is the scale here is 1 to 4. So for our 15-inch diameter, we've got about 1.1 square feet. Again, effective area. 8-inch down to 0.2, and with the plate, the 8-inch down to 0.05 square feet. Just a visual of what's happening to the effective area.
Sure. So as we move, I know, Pete, you have some other applications in the residential world. It seems like we talked a little bit about that. I'll let you expand on what you're seeing there. But this was a job that we did a few years back. It was a science building, and you can see the terminal unit minimums. They were pushing the threshold of our devices all the way down to 35 CFM. I mean, that was the required minimum. 35 CFM for a terminal unit. And we're seeing this more and more, this trend of energy conservation. How do we lower air exchanges in hospital application or healthcare application? How do we go in that direction? Because everybody is looking to be more energy efficient and conserving energy. So I do think that, this isn't a specific case where hey, yeah, we did have this one job that, we really had to get into the nuts and bolts of getting really low flows. But I think we're seeing a trend in our industry that they're pushing this direction where we're going to have these lower flows, and we're going to have to be able to be repeatable. We're going to have credibility here. And I think there's going to be some added discussions to the CX agents, the IORs, inspection of records, and the MEORs to talk about, where a 35 with a 10% threshold plus or minus, and with a 3 CFM, when we're going out and measuring. I mean, those are some of the discussions I think are going to be next in our industry to discuss, okay, where do we really need to be when we're down at these low flows? Are we still going to hold the plus or minus 10%, or is that going to expand based on the range that we're trying to measure? So I think that there's definitely some future conversations that are coming our way as engineers try to get down to these lower thresholds. Pete, you said you saw an uptick in the residential world, right, from what they're trying to measure there as well?
Right. There are some. The trend is to save energy. And try to accomplish some of these green objectives. So we want to minimize, the exhaust air. We want to minimize the amount of outside air coming in while still providing enough fresh air. So people are just getting, the numbers are getting lower, and then they're wanting to see tighter and tighter tolerances on this. So we're seeing this in some brand new requirements on some brand new apartment buildings that have some government money involved, and the specifications are such that they're trying to achieve these particular green objectives. And that's something that needs to be addressed. I'll mention one other point that I think that the industry ought to, in response to this trend where we're trying to identify very, very tight tolerances on some of these low numbers. One thing I think the tab industry might want to consider is the idea that if these particular grills are in the same occupied area, the fact that you've got a 35 and an 80 and a 130, if these are all supplying the same area and you're off by a little bit on the 130, is it really necessary that the 35 be plus or minus 3? Because it might be overwhelmed by what's going on with grill 2-19 there. So I don't have an answer for that, but I'd be interested in a future tab talk type thing that would address that situation.
Yeah, and yeah, this particular application, I unfortunately I don't know the results, guys. I don't know. We handed over our report. We spent a lot of time with Pete and his team. Pete was sent someone up here to help us, go through this testing and witness it with us. and had the MEOR out there and turned over a report. And we went through a couple iterations of the report, did some further testing. We did some transient time of, we introduced smoke to the inlet and saw how long it took for it to actually get all the way through to the supply. Did some other further testing for them, which was very interesting. It was out of the box, things that are not necessarily your typical day-to-day requests, and having Pete come alongside us and help us out. We get hearing, that we're measuring 3 and 5 and 7 CFM just seems just beyond what, we're capable of doing. And that's what, like we already talked about, the repeatability. But it's something that I think that we're getting further down the line in our industry, where I've always heard there's the art of balancing, and then there's kind of the science side of balancing, and this definitely leans more towards the science end of it. And how do we get more scientific in our readings? This isn't, is it going to change the comfort of a room if it's 30 CFM versus 35 CFM? It probably is not going to make much of a difference, especially in an office space or something along those lines. You're not going to notice a difference at that level. But this, getting to be involved in the kind of the more scientific end of it was really eye-opening, especially as we see these trends to lower flow. So, have any closing thoughts, Pete?
Well, I want to thank you again for the opportunity. It was certainly a challenge, and as I said, it prepared us for some other challenges that came afterwards. And it's interesting. I love this kind of thing, and it was a pleasure to be involved with you.
Thanks, Pete. I think we're a little ahead of schedule, but we can go on to the Q&A, Cassie, if you're ready.
Sounds good. We've got some questions coming in already, so people are curious to know more. Thank y'all for that presentation. I'll start at the top here. Steve asks, what is the maximum CFM to read with the low flow plate installed?
The answer is it depends. It depends on the system. And I'm preparing actually a lecture on that topic. But let me just say that what are some of the variables? The variables have to do so the concern is about back pressure in the capture hood causing air in the system to reroute from the grill you're trying to measure and come out some other grill. So one variable is what other grills are on the same duct system? How close are they to the grill that you're talking about? What kind of dampers are in between grill one and the other grills? Are those dampers relatively open so that air can easily move from one grill to another, or are those dampers relatively closed that would represent a resistance to some molecule that wants to change its mind and go out through another grill? The other thing is about the relative pressure in the duct system. The back pressure effect, which means you're going to measure too low because some air is going to go somewhere else. That effect happens usually when the duct system, that is the pressure in the duct, is at a relatively low number, like 0.05 inches of water column or less. That's relatively low. So introducing the resistance, which the airflow capture hood represents an additional resistance over what's usually there. So I'm going to introduce a little bit of a resistance there. But if the pressure in the duct system is relatively high, 0.1, 0.2, then the addition of a capture hood represents an insignificant amount of additional resistance to airflow. And that pressure of 0.1 or 0.2 can just blast through that capture hood like it's not even there. So there's effectively no back pressure effect in that kind of a situation. So you kind of need to know what's going on. Here's an example. Suppose this is a visual. Suppose you're talking about a 2x2 grill, and the tab tech comes up and it's a 2x4 grill. The tab tech comes up and he's got a 2x2 capture hood, and he doesn't want to take the time, or he doesn't have a 2 foot by 4 foot skirt available. He doesn't want to take the time, whatever. He's going to measure that grill that's 2x4 with a 2x2 capture hood. So he's going to go up on one side to make a measurement, and then he's going to go to the other side to make a measurement. It's obvious to everybody that he's going to get an answer that's way too low, because the minute you put that capture hood up there, a whole bunch of air is going to go through the other side, because there's just less resistance there. So that's the image you need to have in mind when you're talking about back pressure. You might be going up a properly sized grill, but there are other avenues for the air to the other routes that the air can be taken, and the degree to which that happens depends on where are the other grills, what's the status of the damper, and what's the pressure in there. So here's what I do. If I can, if I have one of these capture hoods that's using a plate or not using the plate, is I'll take a measurement without the plate, and then I'll take a measurement with the plate. So the measurement without the plate might have the consistency problems that we talked about a few minutes ago. And so you'll have to, let's say that you're at 100 CFM, and you see 90, you see 110, but if you average over time, let's say it comes out to 100, that's without a plate. You put a plate in there, the object of the plate, again, is to get the velocity up higher so I can get a more consistent signal to the sensor, but I'm adding back pressure, right? But if I come up with about the same answer, then I say back pressure is not an issue, because I increased the flow resistance, but the reading didn't change. Okay, but if I put the plate in there and suddenly the reading is a lot lower, instead of 100, I'm getting 80, then it says to me that adding the plate added resistance and caused air to go somewhere else. That's a signal that there is a significant back pressure effect that you need to take into account.
All right, another question. Any restriction on the accuracy of the low flow hood in vertical versus horizontal position?
No, the sensor is position independent, and the air molecules are under such pressure that they're not affected by gravity or anything like that.
All right, we've got several more questions coming in. People are very interested
Okay.
in what y'all have to say. Can you use the same pressure/velocity modules and wrist reporters from the standard capture hood with the low flow hood?
Eventually, you're going to be able to do that. If somebody has an application right now for 5 CFM, we would loan them a special wrist reporter that has the necessary formula in there. And the reason is that we've only seen a few, let's say like less than 5 requests for this. So we haven't made it yet a standard product that would be supported by our production version of the wrist reporter. But if by this time next year we've had 50 requests, then we would go ahead and integrate the necessary factors into the standard wrist reporter, and then everybody would have the same capability. So I'll just say that if you're out there and you have an application and you want to try this out, we'll make special arrangements, and along with the plate that I mentioned and a low flow capture hood, we would provide a special wrist reporter that you could use for that project.
All right, going down the list here. Chuck says, is the flow measurement accurate from a ceiling diffuser, a sidewall grill, and a floor-mounted register?
Yes, the orientation of the capture hood makes no difference to the accuracy of the measurement.
All right, this next one says, Pete, what are your thoughts on the thermal dispersion AFMs? Are they accurate when installed in VAV boxes?
I don't have any direct experience with those. So I can't say. My it was my understanding, and I'll ask Eric and anybody else that might have an opinion there, that there um, that thermal dispersion sensors needed to somehow be protected against collecting debris, by a filter or something like that. That debris buildup over time could affect the reading. But my understanding is that those types of devices, for instance, for airflow stations, that they're very popular and that the quality has gotten a lot better over the past 10 years. So perhaps they've come up with a solution for that. But so the answer is I don't know. But it's something I'm interested in because I'm working over the next 12 months on my own airflow station, and I'll be finding out a lot more about the competition.
I will say that, one of the things that we've seen in new technology is, whether it's new or not, but is the company Accutrol. They use sound, and they measure sound waves to quantify CFM. I was, when I first saw this technology, I said, I don't know how this works, but it was incredibly close to our hoods from what we measured. And I thought the technology was very interesting, in which, they explain it like the ripples in a flag, blowing in the wind, and that's what they're measuring. The accuracy at which they were able to measure CFM compared to our hoods it was incredible. So definitely some new technology out there.
All right, next question says, AABC and NEBB standards indicate that a flow capture device is a tool for proportional balancing and indicate that factors are required to be applied to determine true CFM. Does the low flow hood measure true CFM?
So so that statement is correct, and that statement addresses itself to the back pressure problem that I was talking about a few minutes ago, and it addresses itself to a discussion about how much back pressure is causing in a particular situation, how much air is being diverted. So the suggestion that you've got to check the CFM with a NIST traceable velocity traverse, which, by the way, usually requires some degree of straight duct. So yes, that's the preferred method. Take a measurement of CFM through a velocity traverse. That's your number. Go around, measure all the grills in the area, and come up with a number that may be about the same, or it may be lower by 10% than what you saw with the velocity traverse, and then apply that particular factor to the individual measurements. That is the tried and true scientific way to do it. Now, as every single tab technician knows after a few weeks, is that you don't have an ideal place to do a velocity traverse. And sometimes you don't have the time to make that effort. So I think that there are cases where the practical thing to do is to use the capture hood and your experience to decide whether you can trust the number to within a few percent, or if you can't trust the number, know that that's what you got to do. You got to go back, make a good, the best possible velocity traverse, and compare the velocity traverse to the sum of the CFM that you're getting from your capture hood. Let me have Eric talk to that subject.
Yeah, I mean, we know that technology is definitely increasing. I think Pete's kind of on the forefront of watching capture hoods and what he's trying to do and innovate. I think some of the test and balance world has kind of been stuck in old technology, and we're trying to increase that. And traverse will always be our number one. Pitot traverse is always going to be our number one accurate way to measure airflow. And to Pete's, to his description there, that's what we should be doing, right? We should be looking at the pitot traverse versus our capture hood, coming up with a K factor and applying it as we go and do our balance. Typically what we see when even doing that is that those readings are fairly close to one another most of the time. There's probably been a few applications that I wanted to bring up to Pete, different types of grills that we've seen that has skewed some of our readings, some maybe for another web talk someday. But for the most part, it seems like we're within that 5% range, and can kind of move forward with knowing that even, the specifications plus or minus 10%, and we're measuring plus or minus 5% from according to our pitot traverse. We can be pretty confident that we can move forward with that tool in reading CFMs and moving forward, reporting that into our reports, our tab reports.
All right, next up question. David says, love that we can attain stable readings for low flows in commercial applications. However, do you feel the desired airflow diffusion performance index, ADPI, needs to be addressed with the consultant?
Erica, maybe I'm not sure if that's for you or for me. I'm not exactly sure about that terminology.
Yeah, I haven't heard of ADPI. I'd like to know more about that for sure.
All right, I'm gonna move on to the next question, but David, if you want to add any more in the Q&A about your question, we can pitch that back to Eric and Pete. Our next question says, does the low flow plate come standard with the equipment? I apologize if this has been mentioned and I missed it.
Not at the moment. I would be happy for somebody to contact me and talk about his application, and we would provide it on a case-by-case basis. If 12 months from now there's been it becomes a popular application, then we'll make it a standard. At the moment, it's kind of a special product for special situations. But we're always a little careful when we introduce a new product. We'll provide it to 5 people, 10 people. We'll getting feedback. Is it working the way you want it to? Or there's some other features you'd like to have? And so we're in that stage where it's not a standard product yet, but it could easily be. We just need to see how popular it's going to be, and see if the current features are sufficient to everybody before we productize it. That's where we are right now. It's like a pre-production status.
And I think you spoke to this earlier, but you do have lower or plates for the 3-pound hood, correct?
Yes. Okay. Yeah. So that answer was with respect to measuring 4 or 5 CFM. So we have a product called the 3-pounder that is it's a very lightweight capture hood, and it's a very big capture hood. The base is 1.8 square feet, so it's 50% larger base than a standard size capture hood. So it can handle up to 3,000 CFM on the high end. That capture hood does come with 2 standard flow adjustment plates. One for use at around 100 and the other for use at around 30 CFM. So you'd be going along and using the hood. You're measuring, let's say, 200, 400, 600 CFM with no plate whatsoever. You come to a situation where there's only 70 CFM, and you can quickly install a flow adjustment plate that changes the range of the capture hood measurement down into that region where you are without causing too much back pressure. So it allows one capture hood to address a very wide range, as I said, from 30 CFM to 3,000 CFM through the use of these two plates. So that is a standard. We're shipping it. The standard risk reporter supports that. It's just, I was answering the question before about the 5 CFM plate for the low flow capture hood. That's not a standard product yet.
All right, it looks like that is all the time we have. Thank you so much, Eric and Pete, for an excellent presentation and wonderful discussion. And thank you also to Evergreen Telemetry for sponsoring this webinar. Last but not least, thank you to everyone who joined today. Before we wrap up, one small correction to some housekeeping from earlier. Certificates will be sent out within 48 hours after this webinar. And I also want to remind everyone that registration is open for the AABC annual meeting happening in just a few weeks. That's October 9th through 11th in Lost Pines, Texas. We hope that you'll join us, and you can visit aabc.com to register. That's all for today. Thank you so much for your time, and we'll see you at the next webinar.
Thanks, everybody.
Yes.
Thanks, Eric.
Yep. Thanks, Pete.